Alright, today we are going to be working with discontinuities on our graph, or locations where our function is not continuous. You are going to want your graphing calculator out for this unit, so go ahead and take that out now if you don't have it sitting next to you. So a discontinuity is a point at which the function is not continuous. To think about not continuous, think, do I have to pick up my pencil in order to keep drawing this function? Okay? It's going to be a value at which the function is undefined. Well, we find values that are undefined based off of our domains. So for our rational functions, we're going to consider the places where the denominator is equal to 0. That's going to be our focus. But with any function, if you have a value in your domain that's not defined, there's going to be some sort of a discontinuity for some reason. So I'm going to have you draw this graph on your paper the best that you can. It's going to look a little bit funky, but we'll talk about the different pieces of it. Okay, so this graph right here represents our three different types of discontinuities. This first one is called a jump, and jumps happen often on piecewise functions, which we studied in a previous unit. This one right here is a vertical asymptote. A vertical asymptote is a vertical line, so it's always going to be written in the form x equals a number. In this case, it would be x equals -1. This right here represents our last type of discontinuity, which is a hole in the graph. So this we would say our hole is at x equals 1, and the hole is 1, 1, because this is the value that you would be able to find if you could plug in 1 in your function. We're going to focus mostly on vertical asymptotes and holes. We're not going to worry so much about the jumps for this unit. Alright, so the first one we're going to focus on is a hole, a value at which the denominator of a rational function, remember rational written as a ratio, is equal to 0. Okay, well that's how we found domain on our previous examples, but in this case that factor is going to cancel with a factor in the numerator, and that will define where we have holes in our graph. So let's start by looking at a function. We're going to look at the function f of x equals x squared minus x over x minus 1. Now I want you to go ahead in your graphing calculator, type that in to your y equals. So we've got x squared minus x divided by x minus 1. And if we look at that function, it looks to be the line y equals x, right? Over 1, up 1, over 2, up 2, etc. But if we look at our table feature, so go ahead and press second graph to get to the table, and we go to the value of x equals 1, we have an error. Okay, we do not have a value that's being spit back for y. This is what's happening on our graph. You want to start by simplifying your rational function by factoring the numerator and the denominator. So this is going to be x times x minus 1. In the bottom, it's just x minus 1. That can't be factored. So our domain here is going to be all real numbers with x not equal to 1. That means our graph, though, is going to have a hole at 1 because this problem spot, this x minus 1 factor, cancels with what's in the numerator. So at 1 we're going to have a hole, but the rest of our graph is going to look just fine. But we're going to have a hole right here at 1. Now to find the value of this spot, we know that it's happening at 1. Then when you plug 1 into your reduced function or your simplified function, we get 1, so there's a hole at the point 1, 1. Okay? Thinking about it from an equation point of view right here, without looking at the graph, we have f of x equals x plus 2 over x squared plus 7x plus 10. First thing we want to do to see if there's any holes is to simplify by thinking about our factors. So we have x plus 2 over x plus 5, x plus 2. So looking at this, we have two possible places for discontinuities, -5 and -2. One of these is going to be a hole, and the hole is going to happen at -2 because those can cancel out. So there's a hole at -2. When you cancel that out, this numerator is just 1. To find the value, I'm going to say -2, comma. When I plug -2 into this simplified function, I get 1 over 3. Okay? Next one are the non-removable discontinuities. Okay, you have to do a little more work in order to be able to remove them by redefining more things in your function than just canceling out one factor. So the first one is a jump, but I told you we're not going to focus on those here. What I do want to focus on is a vertical asymptote. So just like a hole, it's a value at which the denominator of a rational function is 0. So we're thinking about domain, all of that. But in this case, it will not cancel with a factor in the numerator. So we're going to skip this graph for right now. I want to talk about the vertical asymptote that is going to exist in this function that we had on the previous slide. So you already have this in its factored form. We know that these are going to cancel out. So our vertical asymptote is going to be our other problem spot. This problem spot right here is going to be when x equals -5. And because we're looking for a vertical asymptote, we write it as the line x equals -5. Okay, this graph was just left over from the previous example. My apologies. So, sketch a graph of h of x. Use a graphing calculator with a window and look closely. So, on your graphing calculator, I'm going to have you type in that function under the y equals. So you can clear out our previous function. Make sure you keep the whole numerator in parentheses and the whole denominator in parentheses. Alright, and then when you press graph, go ahead and change your window so that it fits what's provided for you. And then I want you to try to answer the 3 questions below. So go ahead and pause your video now. Alright, hopefully your graph came out like this, matches the calculator, and I just redrew it on the paper, or on your smartboard. So at what value does x have a vertical asymptote? There's a vertical asymptote at 1, so we write it as the line x equals 1. At what value of x is there a hole? Well, there's a hole at -4. Estimate what the y-coordinate of the hole should be, -1/5. You can do that from looking at your table. Now, if we think about this analytically, and I take h of x and I factor it, I'm going to get x plus 4 over x plus 4, x minus 1. So there is a hole at x equals -4 because that one cancels out. When you cancel that in the numerator, you just get a 1. Then, to figure out the y-coordinate, I'm going to take -4 and plug it back in for x. 1 over -4 minus 1 gives me 1 over 5 negative. Then, to find the vertical asymptote, after we've canceled out the hole, this x minus 1 is causing a discontinuity in our graph. There's a domain problem there, and that causes our vertical asymptote. Alright, find all holes and vertical asymptotes. So first thing you always want to do is simplify your function as much as possible. So this is going to factor into x plus 4, x minus 4, x plus 4, x minus 3. So our domain would be all reals, x not equal to -4, x not equal to 3. Okay, you read your domain from your original function. But our hole is at x equals -4. Specifically, it's going to be the point -4, comma. When I plug in -4 here, I get -8 over -7, so that's going to be 8/7. Then, whatever's left in the denominator that's causing us a problem, there's going to be a vertical asymptote at x equals 3. Alright? Next one, first thing, try to simplify as much as possible. The top isn't going to factor, so that's just 2x squared. On the bottom, I get x and x plus 1. So here, my domain would be all reals x not equal to 0 and x not equal to -1. Read your domain from the original function. Then, to start thinking about holes and asymptotes, well, I can cancel out an x with an x up here, which means that there's a hole when x was equal to 0. Okay? Specifically, it's going to be at the point 0, comma. When I plug in 0, I get 0 over 1, which is still 0, because this is dropped by 1 power. Then, thinking about vertical asymptotes, what's left in this denominator that's causing us a problem? The line x equals -1. Okay? Again, first step, go ahead and factor the numerator and the denominator. This is going to be x plus 3, x minus 2. Down here I can take out an x, and I'm left with x squared plus 2. So thinking about domain, I would have all reals with x not equal to 0. And here I would have x not equal to the square root of -2, which would be plus or minus 2i, which means this factor right here is not causing us any problems as far as discontinuities are concerned. So thinking about holes, is there anything that cancels in the numerator and the denominator? Hopefully you answered no. So we know that there are no holes. Vertical asymptotes, what are our problem numbers on the bottom? Well, we're going to get a vertical asymptote. Oops, I already wrote that. Vertical asymptote when x is equal to 0. And then if you doubt yourself, you can set this equal to 0. We know it didn't cancel with anything in the numerator. So to check if it's a vertical asymptote, plus or minus the square root of 2i. Well, that's not going to be something that we plot on our real coordinate grid. So this does not count as a vertical asymptote. It's not causing us any discontinuities. We just have a vertical asymptote at x equals 0. Alright, last one. You can go ahead and think about simplifying this one if you want to as x minus 2, and x minus 2. So hopefully looking at that, you're telling yourself I have a serious domain problem. All reals, but x can't be equal to 2. Is there anything that cancels in the numerator and denominator? No. So there are no holes. What is the problem spot that's left over? Well, from all of these, we are getting a vertical asymptote at x is equal to 2. So again, the method for all of these, factor, okay? Factor your original function. Think about your domain being from just the denominator. We're going to focus on domain again later. Then, after you found your domain, start canceling things. Things that cancel result in holes. Take that x value, plug it back into the reduced function or the simplified function to get your y value. Anything that's left over that's causing a problem spot is going to create a vertical asymptote at that value.